So we've learned in the past that exponential models are a great way of looking at growth, especially population growth. Things grow exponentially, except for when bad things happen. And we all know that if things are going well for a while, something bad's coming along the pike. But here's what this is. Logistic growth is basically a way of showing the growth of a population. And by population, I might mean human beings. I might mean bacteria in a culture. I might mean fish in a fish tank, or even fish in a pond, which is like a very large fish tank, just naturally made. Okay? It's about a population, but we all know that as populations grow and grow and grow, suddenly resources become scarce. Or maybe, I don't know, diseases might start running rampant, even a pandemic occasionally. So, what happens is usually in any environment, there's what we call a maximum level of population growth or a population. That's called the carrying capacity. You may have heard this in a biology class before. It's not going to be a perfect straight line. This is what it looks like mathematically. It's really a graph that's sandwiched between two horizontal asymptotes, mathematically speaking. The bottom horizontal asymptote is kind of obvious. That's zero. Population's not going below zero. And there's a good chance that when we started looking at things, there's probably more than one animal there, or probably more than zero, because we needed to start the population growth. Also up top, that carrying capacity, which we use the capital letter L for, the limit, the carrying capacity, well, that is not a nice flat line in reality either. You know, populations go up above that and below it, but generally if you go above, that's when famine starts, maybe a war, possibly more predators move in, maybe there's just a lack of food and starvation occurs. Generally, there's a top limit to the population in any kind of population. So here's the equations for logistic. This is what it looks like. Notice that it does involve an exponential function there because, like I said, the first half is like exponential growth. And the second half is sort of like an exponential function just transformed. But this is the equation that we have where L is the limit or carrying capacity, and B and K are different constants. Now those constants could make this grow higher, it could make the curve steeper or more pronounced horizontally. It might take longer to reach that carrying capacity. They are different. And to find this differential equation, well, we could work backwards. And we could solve the differential equation just like we've done throughout most of Chapter 6. However, this is very difficult and time-consuming. So as much as it pains me to say this, it's actually better to just memorize this differential equation and what the original equation will look like. If you'd like to see how you can solve this, please take a look in Chapter 6, Lesson 3, and they have a very nice proof showing it. But it's not easy to remember, and it takes time to do. So best, especially for the AP exam, to memorize these two equations so that you will always know what you can use to find either the slope or the actual population. The first simple calculus thing I would like you to remember though, and this should be very easy, if you ever take the limit where time goes out infinitely far, you can plug all of this in and you'll get the right answer, or you can just realize, wait a second, that's just going to be my carrying capacity. It's going to hit that upper level. If this is truly a logistic equation, as time progresses, it will always hit that upper level. And now one example of what this might look like in a question. Now here's some other problems that were once found on an advanced placement exam. They started giving you this equation, not telling you it was logistic, but they asked two separate questions. If you have an initial condition at 3 or 20, what's the limit? And if you were wise, you could actually put down, no matter what the initial condition, the limit is 12. That's the carrying capacity. Look how it matches up down here. L equals 12. K is 1/5. And this is all set up very nicely. A second question asks, at what population when is the population growing the fastest? At what value of P? Well, that inflection point is growing fastest always at the midway point.